Hello everyone. In this section we are going to discuss about alpha beta cutoffs. In the previous structure we studied about minimax algorithm. In minimax algorithm we use depth first process and the main disadvantage of minimax algorithm is that it is not possible to find an output without visiting entire nodes in that tree. Alpha beta pruning is a modified version of minimax algorithm. It is a process of cutting the nodes as we know that the path through that node doesn't produce a valid output. So the main advantage of alpha beta pruning is that here we should not visit entire node. Instead we are able to prune some paths that are not necessary. So we have two parameters, or it is also called threshold values, alpha and beta. Alpha indicating the maximum value and beta indicating the minimum value. So in there is two players, a player and an opponent player. So here we assign a max player and min player in each levels of this tree. So in max level or max play, the alpha values get updated and the min level the beta values get updated. So what is known by alpha beta pruning? To modify our search procedure slightly to handle both maximizing and minimizing players, it is necessary to modify the branch and bound strategy to include two bounds, one for each of these players. The modified strategy is called alpha beta pruning. It has two threshold values representing the lower bound on the value that a maximizing node may be assigned. So that is indicated by alpha. So alpha is the lower bound on the value that the maximizing node may assigned. So alpha is a maximizing node. So what is the worst case to alpha is that is negative infinity. Alpha is assigning a positive value, but we assign in lowest value, that is the lower bound for alpha is negative infinity, and the upper bound on the value that a minimizing node may assign is beta. So beta is called positive infinity. The condition for pruning is that alpha is greater than or equal to beta. So next we are going to see an example for alpha beta pruning. So here is two players, a maximizing player and a minimizing player. Maximizing player always try to increase the value and the minimizing player try to decrease the value. Here is the example. In this example, we apply depth first process and we reach the depth of the tree. And to calculate the value of alpha and beta at node B, we compare the two subtrees D and E. The values of D and E is 3 and 5. Then comparing, then we get the minimum value is 3. So we given the minimum value of 3 to B. And these values, then we do backtracking and we get reach A. Here the value of alpha should be updated because A is a maximizing play and B and C are the minimizing play. In maximizing play we update the value of alpha, and in minimizing play we update the value of beta. That is why we update the value of beta in the node B, and alpha should be remained same. And when reached to A, there should be update the value of alpha. Then we update the value of alpha as 3, that we get the minimum value from the B, and that will be the maximum value in the node A. Alpha is a 3 and beta is an infinity. And when we reach the right subtree after examining the node F, we know that here the C value of C will be like alpha is equal to, it is a minimizing play, so alpha is equal to minus infinity. So the previously we get the value of alpha as 3. So here alpha is 3 and beta is equal to minus 5. So here is the condition that alpha is greater than or equal to beta. Here 3 is greater than minus 5. So we can prove the right node of the C. That means we cannot look to the node G because it doesn't provide a valid output. So we should prune that node. This is the alpha beta pruning indicates. Here is the next example. Here also we doing alpha beta cutoffs. So initially the value of alpha and beta at the node A is minus infinity and beta is positive infinity, and we apply depth first process, and the value to find the value of B, we know that alpha is minus infinity because it is a minimizing plane, and beta value is 3. That is the updated value after noticing the values of D and E, and this value is given back to A, and in alpha it is a maximizing plane, so the value of alpha should be updated, and alpha is equal to 3 and beta is equal to infinity. This value is given to the depth of the tree, that is we look to the node F, and it has a subtree I. So I has two nodes K and L. After K is examined, we see that the maximum score to I is 0, which means the F is guaranteed a minimum of 0. But this is less than alpha's value of 3. So no more branches of I is need to be considered. The maximizing player already knows that the choose to move C and then to I, since if the move is made, the resulting score will be not better than the value of 3. Now let's see how the value of beta can be used. After cutting off the further explosion of I, J is examined, yielding a value of 5, which is assigned a value as the value of the F. This value becomes the value of beta at the node C. It indicates that the C has a value of 5 or less than 5. Now we go to the node G. First M is examined, and it has a value of 7, and which is passed back to G. So there we know that this value is not valid. But now 7 is combined with the beta of 5, it is greater, and the player whose turn it is at the node C is trying to minimize that value. So this player will not choose G, which would lead to a score of at least 7, since there is an alternative move to F, which will lead to the score of 5. Thus it is not necessary to explore any of the other branches of G. From this example, we see that the maximizing levels we can rule out and move early to if it becomes clear that its value will be less than the current threshold. That means the current value of the node. While at minimizing level, search will be terminated if the value are greater than the current value are discovered. But ruling out a possible move by a maximizing player actually means cutting off the search at the minimizing level. So we relook the previous example. Here, once we determine that the C is a bad move from A, we cannot bother to explore G or any other paths at the minimizing level below C. So the way alpha and beta are actually used is that search at a minimizing level can be terminated when a value less than alpha is discovered, while a search at the maximizing level can be terminated when a value greater than beta can be found. The next we look to the example from minimax procedure. this is the same example that taken from the minimax procedure that we earlier discussed. Uh, so uh, so taking this example, we are going to modify this minimax procedure that we discussed earlier using this new technique of alpha beta pruning. Notice that at maximizing levels, only beta is used to determine whether to cut off the search, and a minimizing levels only alpha is used. But at maximizing levels, alpha must be known, since when a recursive call is made to minimax, a minimizing level is created. The minimax procedure as it stands does not need to treat maximizing and minimizing levels differently, since it simply negates evolutions each time it changes levels. Instead of referring alpha and beta in minimax, we use as two values, use thresh and pass thresh. So the use thresh and pass thresh indicates the alpha and beta in our modified minimax algorithm. Use thresh is used to compute cutoffs. Pass thresh is merely passed to the next level as its use thresh. So here we see that the alpha values, beta value is passed to the next level as the alpha because of the difference in the maximizing and minimizing players. So here also, instead of we use alpha and beta, we use thresh and pass thresh. So use thresh must be passed to the next level, but it will be passed as the pass thresh, so that it can be passed to the third level down as use thresh again. Okay, then we taken the example of 12.4, that is here at the maximizing level, such as that node A alpha is said to be value of the best successor that has yet been found. Notice that at maximizing levels, it is the beta that is used to determine cutoffs. It is the alpha whose new value can be computed. So the important thing to notice that at the maximizing levels, beta value is cut off and alpha value is updated. Okay, and thus at any level, use thresh will be checked for cutoffs and pass thresh is updated. But if the maximizing node is not at the top of the tree, we must also consider the alpha value that was passed down from the higher node. And we look to the example of 12.5. Here we assign a value 0 to node I on the basis of examining node K. This is so far the best successor of F. But from an earlier explosion of the subtree headed by B, alpha was set to 3 and passed down from A to F. Alpha should not be reset to 0 on the basis of node I. It should stay as 3 to reflect the best move found so far in the entire tree. Thus, we see that at the maximizing level, alpha should be set to either the value it had at the next highest maximizing level or best value found at this level, whichever is greater. The corresponding statement can be made about beta at minimizing levels. In fact, what we want to say is that at any level, pass thresh should always be the maximum value it inherits from the above and best move found at its level. If pass thresh is updated, the new value should be propagated both down to lower levels and back up to higher ones, so that it always reflects the best move found anywhere in the tree. And we use a function minimax AB, which requires 4 arguments, that are the current position, the depth, use thresh and pass thresh. here we can see that the minimax function, and what are the arguments assigned to that are given in this example. So the initial call to choose a move for player 1 can be given as minimax a b, current 0, player 1, maximum value static and update, minimum value static and update. This is the process of defining the minimax function. So next we are going to discuss about the algorithm for minimax function. So we already said about the position, depth, player, and use thresh and pass thresh indicating alpha and beta. So in step 1, we use a function deep enough, and it has two arguments as position and depth, and we check that initially the value of depth is 0, then return the structure and the value, assign the value as static, and the position and player is assigned to that. Path is nil. And in second step, we notice that if the case that is not empty, generate one more ply of the tree by calling the function move gen. It has assigned the parameters position and player, and getting the successors. So here we try to find the successors of a node. If successors are empty, if there is no successors, there are no moves to be made, so we should return to the function back, and if there is successors are not empty, then go through it, examining each element and keeping track of the best one. So here we have the following steps to be followed. For each element, to find the successors, in the first step, set the result of suck to the function as minimax ab, and suck comma depth plus 1 comma the opposite player is given, and also their pass thresh and use thresh values are given. And the next step, set the new value to value of result suck. The new value is set to value of result of suck. If the new value pass thresh, then we have to find a successor that is better than any that have been examined so far. So record this by doing the following steps as to find the any successor that is better than the previously examined. Set the pass thresh to new value. The best known path is now from current to the sucker, and then on the appropriate path from suck as determined by the recursive call of minimax AP. So set best path to the result of the attaching suck to the front of the path of result of suck. This is a procedure to find a better successor than we already found out one. And in the last step, if we pass, if the pass thresh, that means reflecting the current best value, is not better than the use thresh. That means in the previous section we said that the beta value is not best than the alpha value available. Then we should stop examining that branch. That means we can cut off that branch or prune that branch, but both threshold and values have been inverted. So if the pass thresh greater than or is equal to use thresh, then return immediately with the value. That is the same thing where we said that alpha is greater than or equal to beta, we can prune the value. So value is equal to pass thresh, path equal to best path. And in the fourth step, we return that structure, then value is equal to path thresh, and path is the best path. So the effectiveness of the alpha beta procedure depends on the order in which we examine the paths. If we examine the roast path first, then no cutoff set will occur. But if we examine the best path, then we guaranteed that we should not bother about the search process, we can cut off the unwanted nodes too. If, however, we know how effective the pruning technique is, it is possible to prove that if the nodes are perfectly ordered, then the number of terminal nodes considered by the search to depth D using alpha beta pruning is approximately equal to twice the number of terminal nodes generated by the search to depth D by 2 without alpha beta. So the idea behind the alpha beta procedure can be extended to cut off the additional path that appear to be at best only slight improvements over paths that have already been explored. So we see in the step 4D this the step 3, the D step, we see that we cut off the search if the path we are exploring was not better than other paths already found. Okay, then we have to consider situation in figure 12.6. After examining node G, we see that the best we can hope for is to move C is a score of 3.2. We know that if we make move B, we are guaranteed a score of 3. Since 3.2 is only very slightly better than 3, we should perhaps terminate our exploration of C now. We should devote more time to exploring other parts of the tree where there may be more to gain. Terminating the explosion of a subtree that offers little possibility for the improvement over the other non-paths is called futility cutoff. So here is an example clearly about a futility cutoff, which terminate the explosion of the subtree which does not provide a better improvement to our output or the resulting path. So that's all about alpha beta pruning, and we also seen about the minimax procedure is updated using this alpha beta cutoffs. So that's all about this section. Thank you.